The question we were investigating in the previous video was, can we find pairs of numbers x and y such that x to the y power is equal to y to the x power? And we said that what this means is that the pair of numbers x and y will commute under exponentiation. And our answer to that question was yes, we can find plenty of interesting pairs of numbers x and y. And before I do some new stuff in this video, let me first review what we did in the previous video. And what we did was we took this single equation, which related x and y, and we parameterized it. And what we did is we stuck in the substitution y is equal to t times x. Or equivalently, the parameter t was equal to the ratio y over x. What that allowed us to do was write down a pair of parametric equations in terms of x and y independently. And we found that our equation for x was that x is equal to t to the power of 1 over t minus 1. That was our first equation. And our second equation was for y, and that y is equal to t to the power of t over t minus 1. And we saw that we can start plugging in different values for t, and the pair of numbers x and y that we get out of that will give us interesting pairs of numbers which commute under exponentiation. And some of the highlights from that is one pair of numbers that we came up with was the square root of 3 and the square root of 27. That is, the square root of 3 raised to the square root of 27 power is equal to the square root of 27 raised to the square root of 3 power. And another interesting thing we found was that if you plug in a value of t that looks like this, for example, 4 over 3 or 7 over 6, where the numerator is one number greater than the denominator, or that the denominator is one greater than the numerator. So if you plug in t equals 3/4, 2/3, or just to combine the two statements, when they differ by 1, when you plug in a rational number that looks like this, the x and y pairs that you get out are guaranteed to be rational numbers as well. So this is essentially what we did last time. And before I do some new stuff in this video, I'd like to make a few observations about this pair of equations here. A few interesting things that I forgot to point out last time. And then eventually what we're going to do, this is going to be the grand finale of this video, is I'd like to return to that equation, x to the y is equal to y to the x. And I make the bold claim that we're going to be able to solve for y in terms of x. And this is the claim that I'll eventually show. But first, let's make a few other observations about what's going on here. The first observation I'd like to make about this pair of equations is what happens when we plug in forbidden values of t. Now, when you have equations that involve ratios like this, you always have to watch out for division by 0 here. So we can see here, down here in this denominator, what value of t would I have to plug in to make this denominator equal to 0? So we have t minus 1 is equal to 0, and we see that the forbidden value of t is equal to 1. So it's meaningless to ask what is the value of the xy pair when t is equal to 1 precisely, when t is precisely equal to 1. However, we can ask what happens to this xy pair when t approaches 1 in the sense of limits. So what we're asking is, what is the limit as t approaches 1 of this x equation here? And let me just copy that down. What is the limit as t approaches 1 of t to the power of t minus 1? And of course, we're making the assumption that this actually goes to something, but let me prove to you that this does actually go somewhere. And the value that it goes to is not at all random. And now, to prove this, let me first make a substitution. I have this t minus 1 here. Let me create a new variable s, which is equal to that t minus 1. So I'm just making a substitution there. So if s is going to be equal to t minus 1, that means t is going to be equal to s plus 1. And now let me make that substitution into the limit here. If t is going to go to 1, that means that s, if I plug in t equals 1 there, s is going to be going toward 0. So I change that to limit as s goes towards 0. For t, I make that substitution, 1 plus s. And then I have 1 over t minus 1. T minus 1 is s. So I've converted this equation to this equation. And if you don't recognize this already, let me make one more substitution, that u is equal to 1 over s. I'll introduce this new variable u. Now if s goes towards 0, that means that u must blow up to infinity. So now the limit goes, as u goes to infinity, of 1 plus, now s is going to be equal to 1 over u. And then I have that 1 over s there, and that's equal to u. And these two equations here, this equation and this equation, are the definitions for a very special number called e. So that's pretty interesting here, that the limit as t goes to 1 of this equation is equal to e. So what that means is that we've just found yet another equivalent way of expressing Euler's number. And now, if we go back to our parameterization, which is y is equal to t times x, t is going to be going toward 1. Now, if I make that substitution, t is equal to 1, or t is going toward 1, really, that means that y is going toward x. That y and x are getting very, very close to one another. They're getting infinitesimally close to one another. Now, if x is going toward e, that means the equation for y must be going toward e as well. So we see that the limit as t goes to 1 of the equation for y, which was t to the power of t over t minus 1, is also equal to e. So what we've observed here are two additional equivalent definitions for e, as opposed to the ones that are commonly presented. That's the first new observation. And the second observation I'd like to make is a little bit more subtle. And I'm going to prove it to you as a theorem that if t is a rational number, then the pair of numbers x and y that I get out are going to be algebraic numbers. And let me refresh your memory on what an algebraic number is, or maybe you haven't heard of it and you'll learn what it is now. So an algebraic number is a number which can be expressed as a root of a polynomial equation. Now, that may sound a little bit complicated, but it's actually not. Most of the numbers that you, well, I shouldn't say most of the numbers, but many of the numbers that you've experienced before are algebraic numbers. And one good example is the square root of 2. And we say that this is an algebraic number because I can express x being equal to the square root of 2 as x solving the following polynomial equation. X squared minus 2 being equal to 0. Because you see here, if I square both sides of this equation, I get x squared is equal to 2, and 2 minus 2 is equal to 0. So an algebraic number is one which can be defined up in terms of a root to a polynomial equation. In this case, the square root of 2 can be defined as the root of this following polynomial p. In this case, it's a degree 2 polynomial. And another good example is the imaginary unit, x equals I. And let's see what polynomial equation that solves. If I square both sides, I squared is going to be minus 1, and I get x squared plus 1 is equal to 0. So I can say that I is an algebraic number because it solves this following degree 2 polynomial equation. Or I could say it's the root of the polynomial x squared plus 1. So that's just what an algebraic number is. And I should also say, too, that the polynomial equation that we want these algebraic numbers to solve has got to have integer coefficients. So that's just what an algebraic number is. So the claim is that if t looks like this, if it's a ratio of two integers, a over b, then x and y that I get out of these two equations are going to be algebraic numbers. So let me prove that now, and it's not too difficult to show. So let me play around with this equation for x. So I make the substitution that t is equal to a over b, where a and b are both some integers. So it's going to be a over b raised to the, I'm going to use this up arrow notation for the exponent. It's going to be 1 over a over b minus 1. So let me figure out what that denominator is. So I have a over b minus 1, which is b over b. So I just combine the two, and what I get out of that is a minus b over b. But I've got to take the reciprocal, 1 over that. So I'm going to take the reciprocal of this and stick it into the new exponent. So I'm going to get x is equal to a over b raised to the power of b over a minus b. And that's still equal to x. And now let me convert this back to our usual notation. A over b to the power of b over a minus b. This is equal to x. Now what we're going to do, I'm going to raise both sides to the a minus b power. So let me write that there. Raise it to the a minus b power. So what I'm going to get is x to the power of a minus b is equal to a over b raised to the, what's left, b power. And let's observe what we have so far. We have x raised to some integer power, and this is going to be an integer power because a and b are both integers. And then on the right-hand side, we have some rational number raised to an integer power. So we have some rational number over here on the right. And now the last thing I have to sort of worry about here is whether a minus b is going to be a positive number or a negative number. Now there are two cases. If a minus b is positive, or it's greater than 0, this x to the a minus b, it's going to look something like x to the third or x to the fourth, something like that. If it's like this, then I'm all set. And let me show you why. So I have x to the a minus b power, but what I'm going to do now is I'm going to rewrite this as a to the b power over b to the b power. I'm going to multiply both sides of this equation by b to the b power. So on the left here, I have b to the b power times x to some positive exponent is equal to what's left over here, which is a to the b power. And now the last step is I'm going to move this thing over to the left-hand side. So I have b to the b power times x to the a minus b power minus a to the b power is equal to 0. And now I claim this demonstrates that x is an algebraic number because we have some degree to the equation here. We assume that a minus b is some positive number. This coefficient here is an integer. It's just an integer raised to an integer power. And this thing over here is also an integer. So x is algebraic. And that's all I have to show for that one. And then this other case I have to worry about where a minus b is less than 0. It's very easy to show this. The only thing you're going to have to do is you're going to have to go back to this equation, that x to the a minus b power is equal to a to the b power over b to the b power. Now if this is a negative number here, to convert a negative exponent to a positive exponent, I just have to take the reciprocal of that. So when I take the reciprocal of both sides, I'm going to get x to the b minus a power. And now since I've taken the reciprocal there, I'm guaranteed that if a minus b is a negative number, that means that b minus a is a positive number. And then the argument just essentially becomes what we have here. Just do some more rearranging. And I take the reciprocal of that right-hand side, and I get b to the b power over a to the b power, and then I just rearrange as usual, and then I come up with a slightly different polynomial equation here with a different degree. Instead of a minus b degree, it's going to be b minus a degree. So this would show that x is algebraic. And then the last thing I have to show is that y is algebraic. And that's not too difficult to show, because we go back to our parameterization that y is equal to t times x. And that means that y is equal to some number, a over b, because we said that t is going to be equal to a over b. That was the assumption. Times x. And now the last observation I have to make is that any rational number is also an algebraic number. And we've already showed that x is an algebraic number. And it's also a theorem too, if you'd like to prove that yourself, that the product of two algebraic numbers, let's say a and a, produces another algebraic number. So that means that if t is an algebraic number, which it is, all rational numbers are algebraic numbers, and if x is an algebraic number, which we just demonstrated here, then it must follow that y is also an algebraic number. So that's just one additional observation about this pair of parametric equations here. But the significance of that is, let's say I give you some t that's equal to, let me give you a numerical example. Let's say 10 divided by 17. Now you see that t is a rational number. So that means that the x's and y's that we get out are going to be algebraic. But you can also say something more than that. One thing you can observe here is that 17 minus 10, I just take the difference of numerator and denominator, that's 7. And what you can conclude from this is that x and y are going to solve a degree 7 polynomial. And how did I know that? Because remember in that proof, we were considering numbers of the form a over b. And then in the course of that proof, we ended up getting a polynomial equation which had x either to the a minus b power or b minus a power. And that's precisely what I did here. I just took the difference of numerator and denominator, and I got 7 here. And that's how I got to the conclusion that x and y, even before I do any sort of computation, I know that they're going to be solutions. They're going to be roots to a degree 7 polynomial equation. And to take an actual example of one example of where we've seen this before is, remember when we plugged in t is equal to 3. Now 3 is a rational number. I can also write this as 3 over 1. What's the difference of 3 and 1? That's 2. And remember what the xy pair that we got out of this. It was the square root of 3, square root of 27. And just following this logic, the difference here is 2. And we see here that what we get out are indeed square roots. And all square roots solve a degree 2 polynomial equation. In the case of square root of 3, it solves this polynomial. It's the root of this polynomial, x squared minus 3, and equals 0. And then in the case of square root of 27, that's x squared minus 27. Furthermore, we had that special case of when we plugged in a rational number, which had the form a plus 1 over a, or the numerator and denominator just differed by 1. For example, we can plug in numbers that look like 2/3, 3/4, 10/11, or 12/11, just where the numerator and denominator differ by 1. And by this logic, if they differ by 1, that means that x and y are going to solve a degree 1 polynomial equation. And what does it mean to solve a degree 1 polynomial equation? That means that the number is rational. So you can see here that the theorem that we proved about the algebraic numbers, when t is rational, is more general than that other theorem that we proved about when numerator and denominator differed by 1. So that's enough about algebraic numbers for now. Let me return to that claim that I made in the beginning of the video, where I have this equation, x to the y equals y to the x, And what I'm going to do is solve for y in terms of x. And what that's going to allow me to do is, if you present me with some x, if I can do this, if I can solve for y, I can compute that y. So you present me with some x, and I can find that y that'll commute with it. And in order to do this algebraic manipulation, I'm going to introduce a little bit more machinery here. And what I'm going to introduce is a specialized function called the Lambert W function. And I encourage you to watch my video on that. But just to give you a quick review of what's going on with that, let's say I have some equation here. Y is equal to x times e to the x. Now, what is this equation doing? It's taking some x value and it's mapping it to the value x times e to the x. And what that means is that some number like 1 is getting mapped to 1 times e to the 1, which is equal to e. So 1 is getting mapped to e. And what the Lambert W function is going to do is going to reverse this process. That is, 1 is getting sent to e, but what the Lambert W function is going to do, it's going to input a number, e, and it should map you back to 1. So if I call this forward function f, the backward function, or the inverse, gets the name w. So what the w function is going to do is it's going to give you, you're going to input some value, let's say e, and what the w function is going to output is whatever number such that the output times e to that output gives you whatever number you started with. To make that clear, let's say I take the w function, I stick in the number 1. Now this gets its own special name. It's called the omega constant. And the omega constant is approximately equal to 0.6. But what this means is that 0.6 is the output. So it means that 0.6 times e to the 0.6 is approximately equal to 1. Now the reason I'm introducing this w function is because I want to show you what it's going to do algebraically. Now if I call that forward function f of x, that was equal to x times e to the x, let me give that the name y. Whatever comes out of that computation, I'm going to call that y. Now what the Lambert W function is going to do is it's going to take that y value in and return you with that x value there. Now since y is equal to x times e to the x, that means that w of something that looks like x times e to the x is going to return you x. So what that means is that if you ever see something like w of 3 times e to the third power, because it's of this form, it's something times e to that same something is going to be equal to that something. So that means that w of 3 times e cubed is equal to 3 exactly. So this is the key algebraic property of the w function. At this point, I think we have all the tools that we need to solve this equation. X to the y is equal to y to the x. So I'm going to start by taking the natural log of both sides. So I'm going to get ln of x to the y power is equal to ln of y to the x power. Then I'm going to use the power rule of logarithms just to bring that power out to the front. So I'm going to get y times ln x equals, I'm going to bring that x out front, I'm going to get x times ln y. And now I'm going to move all the x's onto one side and move all the y's onto the other side. So what I'm going to do is I'm going to divide both sides by xy. On the left-hand side, the y's cancel, and I get ln x over x. And on the right-hand side, the x's cancel. I get ln y. And I'm just going to write that as 1 over y out in front, but same thing. And this is precisely what we did in the previous video. We found this relationship has to hold between the logarithms. So nothing radical so far. But what I'm going to do now is I'm going to negate both sides of the equation. And now I'm going to keep that left-hand side the same. I'm going to rewrite it as negative 1 over x times ln x. Now on the right-hand side, I'm going to move that negative up into the power. Just going to use the reverse power rule. So I'm going to write that as 1 over y times ln of 1 over y. So that power just gets moved right up there as a minus 1. And so I get 1 over y inside that argument there. And now what I'm going to do, I'm going to keep the left-hand side the same. Negative 1 over x times ln x. And I'm going to rewrite this 1 over y in a slightly different way. I'm going to rewrite it as e times ln of 1 over y. And I'm going to keep that other factor the same, ln of 1 over y. Now the reason I did that, and the whole reason I negated, is because I wanted that y there to become a 1 over y, so that I can now incorporate the Lambert W function. Because now what I'm going to do is I'm going to take the Lambert W function on both sides of the equation. So I get, on the left-hand side, negative ln x over x. And on the right-hand side, I get w of this entire thing, ln of 1 over y times e to the ln of 1 over y. And now notice what's going on here. We have something raised to times e to that same something here. So when I take the w function of that, what I'm going to get on the right-hand side is ln of 1 over y. And the left-hand side, there's not much I can do with that. So I'm just going to copy that there. And now solving for y is quite simple. So what I'm going to do now is exponentiate both sides. So I'm going to get e to the w of negative ln x over x is equal to 1 over y. And now to solve for y, the last step is to take the reciprocal of both sides. That's the same thing as raising both sides to the minus 1 power. So on the left-hand side, I can just stick that negative in there. Actually, I'm going to move this over to the right-hand side. So it's going to become e to the minus w of precisely what I had before. Now I could leave y as this formula here. This is a perfectly computable formula here for y in terms of x. But when I have e raised to some argument involving the w function, it turns out there's a nice substitution I can make to rewrite this. And to show you what that substitution is, let's say I had some number alpha times e to the alpha power, and that produces some other number beta. Now, from the definition of the Lambert W function, if I take a w of beta, that should give me back to alpha. And now if I make that substitution for alpha in this equation here, what I get is w of some number beta times e to the w of beta should be equal to beta. And if you think about why this is, it's not too radical why this is true. So what I'm going to do now is solve for e to the w of beta, and I'm just going to divide both sides by w of beta. So on the right hand side, I'm going to get beta divided by w of beta. And now I'm going to take the reciprocal of both sides. So that's going to negate that exponent there. And I'm just going to flip the right hand side. So w of beta over beta. So what that means is that if I ever see e raised to the negative w of some stuff beta, I'm allowed to rewrite that as w of that same stuff divided by that stuff. In this case, that stuff that I'm talking about is just this argument here, negative ln x over x. So what that means is that y can be rewritten as w of that argument there, which was negative ln x over x, divided by that very same argument. negative ln x divided by x. And that's all the manipulation that I'll do. And I claim if you give me some value of x that you want to see commute with y, that is to solve this equation, give me that value of x, you compute this to get your y, and that pair of numbers x and y will commute under exponentiation. And again, I encourage you to watch my previous video on the Lambert W function or read a bit more about it. But one subtlety that I should mention too about the W function is that it's what's called a multi-valued function. That is, W of some arguments will actually give you two answers. And both of those answers are perfectly legitimate in terms of finding numbers which will commute like this. So I encourage you to read up about it. And again, watch my previous video to learn how you actually compute the W function. A lot of common programs nowadays have built-in programs to compute the W function, but you can also use Newton's method or a few other methods too to compute this. And I think that'll wrap it up for this video. Thanks for joining me for this video. And in the next video, I'm going to discuss one additional application of this formula, or one additional observation to make about this formula. And it has to do with infinite tetration, for the reason that this formula that we've just derived here is very similar to another formula that also appears when you do infinite tetration. That is, you consider expressions that look like this: square root of 2 raised to the square root of 2 power, raised to the square root of 2 power, square root of 2, and so on. In terms of the formula for determining what this value converges to. So hopefully you'll join me for that. And if you enjoyed this video, feel free to subscribe and stay tuned for more videos.